Okay, so we are on to our next topic, which is control volume analysis. So we're basically going to do conservation of mass and energy for control volumes. We talked a lot in this class up until this point about closed systems, right? Which are mass doesn't change. Now we're going to pivot and talk about control volumes, and control volumes are just open systems where we have mass coming in and out of the system. Okay. So many engineering systems involve the flow of mass in or out of a system. For example, things like water heaters, car radiators, pumps, compressors, turbines, all of those types of systems are going to have mass flow through them. And for these systems, we're generally interested in the rate that mass and energy are being added to or removed from the control volume. And just as a reminder, I put this just below here, but a control volume is an open system, of course, because we're talking about mass coming in or going. And so before we kind of dive into this discussion, there's two definitions that we're going to use frequently throughout this unit. So we're going to just start with defining them. The first one is what it means for a system to be steady. And so steady means that there is no change with time. Mathematically, this means time derivatives of things are zero, right? So if you have a steady system, any equation that has a ddt term in it, you can assume it's zero. The opposite of this is unsteady. Or sometimes the term transient is used as well. All right. So we are going to care about systems that might be steady, and then we also care about flows that are uniform. So uniform means no variation with space. Okay. So I will probably repeat these definitions a couple times throughout the next couple classes just to remind us what these mean as they come up in our discussions. But these are the definitions just out the gate. Okay, so let's talk about conservation of mass first. So we're probably all generally familiar with conservation of mass. And in layman's terms, it just means that mass is conserved, so mass cannot be created or destroyed. I like to think of this as what comes in must go out. All right. So what we'll do to kind of formalize conservation of mass is we are going to look at a control volume that's exchanging mass with its surroundings. So if we have our little blobby control volume right here, so here's our CV. And we're going to draw our control surface around it. So this is our control volume boundary. And to it, we can have mass coming in at 1, and then mass coming in at some other place 2, as well as mass coming out here and here. Okay. So conservation of mass states the following. We have the change of mass within a system. Is equal to the mass added to the system minus the mass removed from the system. Okay. So this essentially looks like the change in mass delta M is the sum of the input mass minus the sum of the output mass. Okay. So we can write this expression for a process that goes from 1 to 2 in the following way. So we can say the mass at state 2 minus the mass at state 1 is equal to the sum of the mass flows coming in minus the sum of the mass flows going out. All right, and so what I mean by M1 and M2 is the mass in the control volume at state 2. And then M1 is the mass in the control volume at state 1. Okay. An important thing to note here in terms of kind of notation throughout this unit is sometimes instead of using M in and M out, we might use the convention ME or MI. So this is mass of the inlet, and this is mass of the exit. And these will have dots on top. So this is, oops. So sometimes we use this convention as just a note here. Okay, but I'll remind you if that comes up, or if there's a question about notation, just let me know. Okay, so if we have a closed system, how would this equation in the orange box change? Can we say anything about the right-hand side or the left-hand side? Yeah. So for a closed system, we essentially have the M2 minus M1 is 0 because M2 and M1 are the same. Or we could say the sum of M in is 0 and the sum of M out is also 0. So we just have 0 equals 0 on both sides of this equation. Which should hopefully make sense because we have fixed mass, right? So a closed system has fixed mass. Okay. It's also important to talk about mass and volume flow rates. So since we care about rates in this unit, so rates at which mass and energy are being added to or removed from our system, we naturally need to know about mass and volume flow rates. So volume flow rate is the volume of fluid flowing through a cross section per unit time. This is typically denoted as volume with a dot over top. All right, so this is dV dt, or the dot means dt. All right, so anytime you see a dot, this means it's a rate relative to time. Typical units are cubic meters per second, liters per second, cubic feet per minute, GPM, which is gallons per minute, and so on and so forth. Hopefully you're all very familiar with volume flow rate after lab 1. All right, and then kind of analogous to volume flow rate, we also have mass flow rate. So this is the amount of mass now flowing through a cross section per unit time. And this is denoted m dot. All right, and the typical units for mass flow rate are kilograms per second or pounds of mass per second. And then we can relate mass flow rate and volume flow rate together. Can anybody think of what we might use to relate them? Oh, that wasn't what I was going for, but I see where you're at. There's another thing that involves mass and volume that's not specific volume, but you are not wrong. Yes, density. So density is mass over volume, right? So we can write that volume is mass over density, which means that V dot is equal to m dot over density, or we can say that m dot is equal to V dot over specific volume. So Mark, you were right, it comes up. So remember, density is just 1 over the specific volume. So Mark, you were completely correct. I just wasn't thinking in the inverse of what I had planned to say. All right. Okay. The mass flow rate of a fluid, so a fluid is a liquid or a gas, flowing in a pipe is proportional to the cross-sectional area A of the pipe or the duct, the density of the fluid, and the velocity component that is normal to the cross-sectional area. So let me just draw this up so that we're all on the same page in terms of terminology. All right, so if this is our pipe and we have our flow with density rho, and then this is our center line. Our cross-sectional area of this pipe is going to be a circle. So this cross-sectional area is A. And then for a circular pipe, this would be pi r squared or pi d squared over 4. Obviously, it would be a different area if it were a duct, because then it would be a square cross section. And Vn, let's give it a different color. Vn is going to be the velocity component that is normal to the area. So that is the velocity component that is perpendicular to this area. So this is Vn. And then if we were to have, for example, if our area was like this and our velocity was like this, then we would have our normal component would look like this. And then we'd of course have a tangential component to VT. Does that make sense? Okay. So using this setup, our conservation or our definition for mass flow rate is equal to the integral over the area of rho Vn dA. So Vn is our normal component to that cross-sectional area. And then dA is going to be a little element, differential element of our area. So this is dA. Okay. And for a circular pipe, dA is just 2 pi r dr, right? As a friendly reminder. Any questions on how we calculate mass flow rate? Okay. Okay. Another thing that we are going to assume in this class for simplicity is one-dimensional flow. So if the flow is normal to the boundary at locations where its mass enters and exits the control volume, and if all intensive properties, including density and velocity, are uniform with position, so uniform relative to position over each inlet or exit area, the flow is said to be uniform or one-dimensional. If this is the case, then that means that we can express our mass flow rate as the following. So we can write it simply as m dot is equal to rho a v. All right, so if we have a one-dimensional velocity, we essentially end up with an integral that is just integral dA, which is just a, right? So we pull velocity out of that integral and then just integrate dA and get a. Okay. I'll write that down just in case. So m dot equals integral of a rho Vn dA. So if the flow is one-dimensional, then we can bring this out and we have m dot, and we can bring out the density because these things are not changing with respect to space. So we have rho Vn integral of dA, which just is m dot equals rho v dA. Okay. In terms of the specific volume, we would write this as m dot is equal to a v divided by specific volume. But if you remember, m dot is equal to v dot over specific volume. So this means that v dot is equal to a times v. Nope, not volume, velocity. Okay. So the two results that are pretty handy here is this one and this one. Okay. Another thing that is very important to note is in all of the control volume analysis that we do in this course, we are always going to assume that 1D flow is an A-okay thing to do. Okay. It's often not okay to do, but we talk about that in ME 3500 if you're an ME student. So the fun continues in ME 3500. Okay. All right, so now let's talk about conservation of mass in rate form. So conservation of mass principle is most commonly used in its rate form. So if we go back to considering our control volume, exchanging mass with its surroundings, so we go back to our little blobby and we give it a boundary, which is this. Then now, instead of just having mass coming in and coming out, we have rates of mass coming in and coming out. So we have now m dot in 1 and 2, and then m dot out 1 and 2. Okay. If we call the mass inside of the control volume at any given time as MCV, then we can write our balance as the following. So we have dmCV dt is equal to the sum of the mass flow rates going in minus the sum of the mass flow rates coming out. We can also write this in terms of the convention I and E, so inlet and exit. So we can also write this as dmCV dt is equal to the sum in of m dot I minus sum exit m dot E. All right, and in words, what we have here is the following. So we have the time rate of change of mass in the control volume is equal to the rate of mass flowing into the control volume through the control surface. So this is the rate of mass flowing into our control volume through the control surfaces. Minus the rate of mass flow coming out. All right, so then we have the rate of mass flowing out. Of our CV through the control surfaces. Okay. So we're essentially saying the same thing that we were saying before, but now we're thinking of it in terms of rates of change relative to time. Any questions so far? Okay. If we are working with a configuration that is steady, we said before that steady means ddt terms are 0, right? So that means that I can get rid of my left-hand side. So this means that dmcv dt is equal to 0. So we end up with 0 is equal to the sum of m dot in minus m dot out. Which we can rearrange as the sum of all the mass flows in equals the sum of all the mass flows out. So just as a reminder, this is only for steady flows. Okay. Okay. If we have steady flow through a one inlet, one outlet device, so these types of devices are things like compressors, pumps, oops, hoses, pipes, etc., etc. Then what we end up with is the following. So we start with our equation that 0 is equal to the sum of m dot in minus the sum of m dot out. And since there's only one input and one output, we have just that 0 is equal to m dot in minus m dot out, or m dot in is equal to m dot out, which we can just call some flow rate m dot, right? Because they're the same. This also means that v dot in over specific volume in is equal to v dot out over specific volume out. If the fluid is incompressible, that means that its volume isn't going to change, so our specific volumes at the inlet and the outlet have to be the same. And then we end up with v dot in is equal to v dot out, which is just some general volume flow rate. Does that make sense? Shall we do an example before we take a break, or do you want to take a break and then do an example? Let's do an example. Okay, there's two examples. The first one's pretty like gentle and short. So we'll do that one first and then we'll take a break. Okay, so we have an incompressible fluid. So this is a fluid where the density is constant and it is flowing steadily through the nozzle of a circular cross section shown in the figure, which I'm going to draw for you. It looks like this. So just imagine you're rotating this around the central axis. It's a pipe of this shape, okay? Like so. Okay, and we have a location 1 and we have a location 2. We want to determine the average velocity at location 2 in terms of the average inlet velocity v1 if the diameter at location 1 is twice the diameter of location 2. So our diameter here is 2d, and then our diameter here is d. Okay? All right. So the first thing that we're going to do is we're going to draw our control volume. So I am going to draw it so that I have a surface, control surface at locations 1 and 2. And then otherwise, I'm just going to have it follow the edge of our pipe. Okay. Next thing we want to do is we want to write our assumptions. Does anybody notice any assumptions in the problem that we can pull out? Anybody? There's a couple that are written for us directly. Yeah, steady. So we have that it's flowing steadily, so we can write that down. So steady flow. I always like to remind myself that that means, oops, sorry, I'm in 3500 mode. ddt is equal to 0, right? What else do we see in the problem statement? Yeah, incompressible. Excellent. And then there's one more that's kind of sneaky. Does anybody else spy like an interesting phrase in there? I won't make you suffer very long. So the phrase that is key right here is average inlet velocity. So if we're talking in terms of averages, this is essentially assuming a uniform flow. Okay. Okay. So next step that we're going to do is we're going to write our governing equation. Which in this case is just conservation of mass. So we have that dmCv dt is equal to sum of m dot in minus sum of m dot out. Okay, and then for step 4, we're going to simplify based on our assumptions. Okay, so we know that steady flow means that our time derivatives are 0, so we can get rid of this guy, right? And then since we only have one inlet and one outlet, we have the following. So we're going to solve. So we have m dot 1 minus m dot 2. So this is the flow direction. I should have drawn that there, is equal to 0. Okay, so this is our starting equation. Let's go back to the problem and figure out what we want to find. So we want to find average velocity at location 2. So we're looking for V2 in terms of V1. All right, so we want to write m dot in terms of velocities, right? So since we want to solve for velocities, in terms of V1, let's write m dot is equal to rho AV, right? Or alternately, AV divided by specific volume. Okay, so this means that we have 0 is equal to A1 V1 divided by specific volume 1 minus A2 V2 specific volume at 2. Can anybody tell me about V1 and V2? Can we say something about them based on our assumptions? They're the same, right? So since it's incompressible, V1 and V2 have to be the same at little v. Specific volume at 1 and 2 have to be the same. Okay, so V1 equals V2 since incompressible. right? So that means that we can multiply both sides of this equation by specific volume and just get rid of it entirely, right? So what we have left is that A1 B1 is equal to A2 V2, or V2 is equal to A1 over A2 times V1. Last thing is I'm just going to substitute in what A1 and A2 are relative to the diameters that were given, right? So we have A1 is pi d 2d squared over 4 divided by pi d squared over 4 times V1. We got a bunch of things to cancel out. So the pi's go away, the 1 over 4's go away, the d squares go away, and we end up with V2 is equal to 4. V2 is equal to 4 V1. Any questions on this problem? So we're going to do another example. This one is a bit more involved, and we're going to tie some things back to what we did with property tables for this one as well. So that you don't feel that we did all that work with property tables for no reason at all, which we didn't. Okay, so we have in this example a feed water heater operating at steady state, and it has 2 inlets and 1 exit. The inlet and exit conditions are shown below, so we have a little figure there. We want to determine the mass flow rates at inlet 2 and at the exit in kilograms per second, and the velocity at the inlet 2 in meters per second. Okay, so we already have a control volume drawn. Oops, that's not what I want. So I'll just redraw in red so that we're absolutely clear that this is what our control volume is. So our step 1 is draw the control volume. We have done this. Next, we're going to list our assumptions. Okay, does anybody spy anything in the problem statement that we might use as an assumption? Yeah, we have steady state again, so that's great. And that is really the only assumption that we can make at the moment, okay? The reason for that is another one that we might want to assume is incompressible, right? We might be tempted, but we're given a bunch of information about temperatures and pressures at the inlets and exits. So that should indicate to us that we probably can't do that, and it's not explicitly said, okay? So we will leave it there at that for now. Our third step is write down our governing equation, which again is just conservation of mass. So we have the rate of change of the mass in the control volume is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out. Since we have a steady flow, that means that d dt terms are equal to 0, so I can get rid of this left-hand side term. Okay? Okay. Which flow rates are our inlet flow rates? One and 2, yes. Thank you. So we have 0 is equal to m dot 1 plus m dot 2 minus m dot 3. Does that make sense to everybody? So 1 and 2 are clearly coming in, and 3 is coming out. Okay. We want to find mass flow rate at inlet 2 and at the exit. So this is m dot 2 and m dot 3 that we're looking for. And we also want to find velocity at inlet 2 in meters per second. So this is V2 that we're looking for, right? Okay, so let's have a look at what we're given here in our picture. So we have that the temperature is 200 degrees C at inlet 1, and the pressure there is 7 bar. That conversion is 7 bar is 700 kPa. And then we also have m dot 1 is 40 kilograms per second. So we have this one, right? For P3, we have that the pressure is also 7 bar. So this is 700 kPa. And we have that, sorry, this is a typo. This should read that V dot 3 is 0.06 meters cubed per second. So just ignore that bottom line. Okay. On the inlet 2, we have the cross-sectional area given to us and the temperature. And then we also have P2 is 7 bar, which is again 700 kPa. Okay. Okay, so we are going to assume that this is 1D flow. Let me do another color. So I mentioned earlier in class, we're going to make this assumption for all the problems that we do in this class. So for 1D flow, we have the following. We have m dot 2 is equal to, hang on, sorry, m dot 1 is equal to rho 1, A1, V1. M dot 2 is equal to rho 2, A2, V2. And then m dot 3 is equal to rho 3, A3, V3. Okay, so we already have m dot 1. This is 40 kilograms per second. And then for the outlet M3, m dot 3, we're pretty close because we already have V dot, right? So for m dot 3, since we already have V dot 3, we can use the following. M dot 3 is equal to V dot 3 divided by the specific volume at 3. Okay, so we know this, but we need to find specific volume at 3. Any ideas on how we might find the specific volume at 3? The tables, yes. Fantastic. We're going to look at the tables. Okay, so for state 3, so we want to find V3, and we know that we are a saturated liquid. So what table should we use? And that P3 is 700 kPa. I see you turning the page, so you already know. So we're gonna use the saturated water pressure tables, right? So a saturated liquid means that we are on the left-hand side line for the vapor dome, right? And we can use our saturated tables, and we will use all of the subscript L values for that point, right? So we just want VL at a pressure of 700 kPa, right? Which is this line right here. And we want, I'm sorry, VF, VL, liquid, fluid, you know. Okay. Uh, sorry about that. So we want this guy, right? Okay. So we have specific volume is 0.001108 meters cubed per kilogram. So I can pop that back in here and I get the following. So I'm going to plug in the V.3 that we have, which is 0.06 meters cubed per second divided by 0.001108 meters cubed per kilogram. Let's first have a look at the units. So the cubic meters cancel. The 1/kilogram flips around to be in the numerator and we get kilograms per second, which is good because that's what we want for MDOT. Those are the units of MDOT. Once we do this 0.06 divided by specific volume, we get 54. No, this goes away. We get 54.15 kilograms per second. Okay, so that's good. That's one more piece of the puzzle that we now have. So that will go in here, which means that now we have the ability to solve for M2, right? So now we can find M.2. So we had 0 is equal to M.1 plus M.2 minus, bless you, minus M.3. I'm going to solve this for M.2 and we get M.3 minus M.1. So we already have M.3, which is 54.15 kilograms per second, minus M1, which is 40 kilograms per second. So we get that M2 is 14.15 kilograms per second. Okay. Okay, so we have solved for mass flow rates at inlet 2 and at the exit. We've sorted that out. Now we want to find the velocity at inlet 2. Okay, so let's figure out V2. And to do that, what I'm going to use is this equation here. So to find V2, use equation star. So we have that M.2 is equal to rho 2 A2 V2, which is A2 V2 over specific volume at 2. And we can solve this for V2. So we have M.2 times specific volume at 2 divided by A2. We are given the area at 2 and we calculated the mass flow rate at 2. So we just need to find specific volume at 2, right? So we still need this. How will we find it? The tables, yay. Okay, so we're gonna use the tables. to find V2. So for this one, we are given, so we know that T2 is 40 degrees C and P2 is 700 kPa. So what should we do first? We need to figure out the state, right? So since we have our pressure table handy, I'm going to go to our 700 kPa. So we have our saturation temperature is 164.95. So T sat at P equals 700 kPa is 164.95. Is it 95 or 4? 95 degrees C. So we are quite a bit below our saturation temperature. So what does that indicate to us? I heard words. Yes, compressed liquid. So this is a compressed liquid. Okay. I did not provide you the compressed liquid tables, but we do not have an entry for this specific combination of, or for this pressure. So we are going to approximate. We're going to approximate V2 as VF at T2. All right. Not at P2, at T2, right? Always by temperature. So we are going to use our temperature table and go to 40 degrees C, which this is our temperature table. We're going to 40 degrees C, and we will use this specific volume. Okay. So we have that V2 is equal to VF at T2, which is 0.001008 meters cubed per kilogram. And I can plug that in back up here. All right. And so when I do that, I get V2 is equal to 5.7 meters per second. Okay. So we still use conservation of mass and kind of the ways that we can represent mass flow rates relative to specific volume and all that good stuff. And then we also incorporated using our tables to figure out missing information that we needed. Okay. Any questions on this problem? Okay. In that case, now we're going to switch to talk a bit about conservation of energy. So that was conservation of mass. Now we're going to talk about conservation of energy for open systems. So in topics 2 and then kind of in topic 3 as well, we talked about conservation of energy pretty significantly, but for closed systems, right? So now that we are considering open systems where mass can flow in and out of it, we need to take another look at conservation of energy. Okay, so for our open system, we're going to go back to our little control volume that is defined by this surface, like so. And now we need to take into account our rate of heat transfer coming in, our rate of work coming in, our rate of energy coming in through the mass that flows in, as well as the outputs of all of those quantities. So we have Q dot out, W dot out, and E dot mass out. Okay. We can express the conservation of energy equation in non-rate form as the following. So this is going to look Very similar to what we looked at before with a couple nuances. So we have E2 minus E1. So energy, total energy of our control of the mass and the control volume at state 1 and state 2 is equal to Q in minus Q out plus work in minus work out plus the energy associated with the mass that's coming in minus the energy of the mass coming out is equal to Q minus W plus E mass in minus E mass out. Close parentheses. Okay, so essentially the same thing as what we had before, but now we're taking into account the fact that as mass is coming in or out, it's gonna bring energy with it. Okay. So that's all that's changed from what we've looked at before. We can also write this in rate form. So essentially we are going to take a time derivative of all of the terms in this equation and we get the following. So we have the time rate of change of our total energy in our system is equal to Q dot in minus Q dot out plus W dot in minus W dot out plus E dot mass in minus E dot mass out. Okay, this first term is just Q dot. This second term is negative W dot. The reason it's negative is because we view work out to be positive. So that's where we pick up the negative sign. And then we're going to keep our E dot for mass in and out as is. All right, so this is our net rate of heat transfer input. And then this is our net rate of work output. All right. So based on what we've already talked about in the other units, we already know kind of how to handle all the terms of this equation, except for our E dot for the mass flow, right? So what we need to do now is expand these energy through mass transfer terms. And that's what we're going to do now. So when mass flows across boundaries, typically work is used to push the mass in or out of that control volume. And so the work that's associated with the workflow, with the fluid pressure as mass is introduced at inlets and removed at exits is known as flow work. So this is flow work. So if we consider a little element of volume V and mass M, as shown below, the fluid immediately upstream is going to force this fluid element into the center of the control volume. And then that can be regarded as essentially like an imaginary piston pushing the fluid in or out of the CV. So we're kind of imagining little blocks of fluid acting as pistons on other blocks of fluid. So what we have here is this is going to get pushed into our CV. And so if the pressure of if P is the fluid pressure and then A is our cross-sectional area of our fluid element, the work done on that little element is defined as the following. So we have the absolute value of the workflow is equal to F times L, and I owe you a picture. My apologies. So if I draw this little fluid element like so, so this is my cross-sectional area A, and then this dimension is the length, and my volume of this little element is A times L, right? So just to connect this with this figure on the left, so my entire volume I'm going to just shade in as green. So that's this block of fluid drawn in 3 dimensions. So this, oops. So the area of this circular surface here is A, and then this distance here is L. Does that make sense? Okay, so our work for the flow is, or our flow work is F times L. And this, so this F is a force. Well, we already said that this force that our little fluid piston is doing is due to pressure, right? So force due to pressure is P times A. So we have P times A times L. All right. And then we might notice here that A times L is our volume, right? So this is equal to volume. So we end up with P times volume. Or we could write this as P times M times the specific volume. Okay. So if we wanted to write this flow work per unit mass, that means that we just are going to divide this whole thing by mass. So, and since we divided by mass, it's specific flow work. So I'm going to give it a lowercase w. And this is just total flow work divided by mass, which is P times V. Another handy relationship is that our rate of flow work is the following. So we have W dot flow. So I'm going back to our non-specific version of this equation, and this is equal to P M dot V. So we're assuming that specific volume and pressure are not going to change with respect to time, but M does. Okay. Okay. All right, so this relationship is the same whether the fluid is being pushed in or out of the control volume. Since any problem involving flow in or out of our control volume will involve flow work, what we're going to do is we're going to separate it from the general W dot term. So we're going to break apart that W dot term in our conservation of energy into W dot that we're used to looking at, plus a term that is from the flow work. All right, so we're going to say that W dot is equal to the flow work, the rate of flow work, plus W dot in the control volume. All right, and the convention, since we need to be careful about convention for signs on work, W dot for flow work that is less than or equal to 0. Less than 0 is an inlet. And if W dot for the flow work is greater than 0, that means it's an outlet. Okay, so work going in is negative and work coming out is positive. Same as how we thought of work before, okay? Okay, So for a control volume with multiple inlets and outlets, we can rewrite our W dot term in the following way. So we can have W dot is equal to W dot for the whole CV plus the sum of the flow work for the exits. So we have M dot E PE VE minus the flow work at the inlets. So we have M dot I PI specific volume at I. All right, and this entire part of this equation is just the same as W dot flow. So this is our net rate of flow work output. Any questions on this so far? Okay. Okay, so now we need to account for the energy of the fluid entering or exiting the CV. All right, so those are those E dot mass terms. We already know that the total energy of a simple system can be broken into three parts. So we can break it into internal energy, kinetic energy, and potential energy, right? Like this. So we have E is equal to U plus KE plus PE, which is internal energy plus 1/2 velocity squared plus G times Z, right? This is the usual way that we break apart total energy since forever, right? And so what we're going to do is for E dot mass in, this is equal to the sum over all the inlets of M dot I, EI, and then the same thing for E dot mass out. So we have M dot E, E, E. Okay, so essentially what we're saying is that we have mass contains energy just in the same way that our simple system in a closed system contained energy. So it will have internal energy, it will have kinetic energy potentially, and also potential energy, right? So it'll still have those three categories of energy that we were used to thinking about before, but it's flowing in, so we pick up our M dot term, okay? Okay, so we're gonna substitute this into our conservation of energy in the rate form. And here is what we get. So this is what we've started from. We have dE dt is equal to Q dot minus W dot plus E dot mass in minus E dot mass out. All right, so this is what we've started with. And I'm going to substitute this expression that we just talked about. Okay, so we keep our dE dt and we have Q dot minus W dot CV plus, sorry, quantity. And then I also have my sum of my exits, and this is our W dot flow. So I have M dot E PE, specific volume at E, minus inlet M dot I PI VI. Okay, so this is just this. All right, so this W dot I'm expanding in the exact same way that we did before. Everybody follows? Okay, perfect. And then I have plus my sum over the inlets of m dot I times my total energy of the inlet. So I have internal energy plus 1/2 VI squared plus GZI. All right, so these all mean the same things as before. So the velocity, V is velocity, Z is any elevation change that we have, and then U is still our specific internal energy, okay? And then last but not least, we have this exact same term, but for our exit. So we have M dot E times our internal energy. So this is the quantity of UE plus 1/2 VE squared plus GZE. Okay, so let me just mark this up a little bit so that it's extra clear. So this is our E dot mass in, and then this is our E dot mass out. Is everybody with me how I've substituted everything? Okay. Okay. So at this point, I am going to remind you about enthalpy. So we've talked about enthalpy before. It's given the symbol H, and it's related to internal energy, pressure, and specific volume, right? So we have enthalpy is equal to U plus P times V, right? So we can write this for the inlet and the exit. So we have HI is equal to UI plus PVI, right? And then for the exit, same thing. So we have HE is UE plus P, I forgot an I here, E and then VE. All right. So if we go back to our equation up here, we notice that we have enthalpy kind of buried in here, okay? So I will just highlight a few things to make that very obvious. So I'm gonna put our terms for HE in pink. So we have UI that we need, and then a PIVI, which is right here. Okay. Keep in mind that for the PIVI, we have a minus sign times a minus sign, so it's still a positive sign. So we still have UI plus PIVI, all right? So this is gonna combine to give us enthalpy for the inlet. And then similarly, for the exit, we have our internal energy at the exit, and then we also have PEVE here. And both of these terms have a minus sign on them. All right, so we're gonna get negative enthalpy. Okay. Okay, so if I make those substitutions, what we end up with is the following. So we have our change in energy of our control volume is equal to Q dot CV minus W dot CV plus the sum of the inlets, M dot of the inlet, enthalpy of the inlet plus 1/2 the velocity at the inlet squared plus GZ at the inlet minus, bless you, the sum over the exits of M dot E times enthalpy of the exit plus 1/2 VE squared plus GZE. Okay. Okay, so we have introduced enthalpy here purely out of convenience, right? So enthalpy combines internal energy and then the pressure times the specific volume in a way that already kind of naturally appeared in our conservation of energy equation. So we can simplify it by bundling those terms together and using enthalpy, all right? And because of that, now we can just use enthalpy directly and not really worry ourselves with the flow work that's happening in this equation. It still exists, but it's just baked into the enthalpy. Okay. Any questions on kind of the evolution of that equation? We're all having a delightful time. Okay. So to summarize, we have conservation of mass and energy for a control volume in rate form given as the following. So conservation of mass, I'm gonna do conservation of mass I'm going to put in red. So we have that the time rate of change of the mass in our control volume is equal to the sum of the inlets, the rate of mass flow in the inlets minus the mass flow rate in the exits, where we have m dot is equal to A V over specific volume, or V dot over specific volume, where this V dot is the flow rate, or sorry, this is the volume flow rate. And then of course, this is the mass flow rate. And then our energy equation is the following. So we have dE dt of our CV is equal to Q dot CV minus W dot CV plus our sum of our inlets. So M dot I HI plus 1/2 VI squared plus GZI minus the sum at the exits, M dot E times the enthalpy at E plus the kinetic energy at E plus the potential energy at the exit. Okay. As a note, at steady conditions, DDT terms go to 0. Okay. So this is essentially the rate form version of the equations that you would get on an equation sheet. This is what you should put on a cheat sheet, or what you should refer to when doing problems like this, okay? For the steady form, I'm not going to rewrite it, but the left-hand sides are just 0. Okay. And then the non-rate form of this, so a process that goes from 1 to 2 would look like the following. So we would have M2 minus M1 for the CV is equal to the sum MI minus ME. And then I should have done that in red. And then conservation of energy is E2 minus E1 equals Q of the CV minus W of the CV plus the sum at the inlets of mass at the inlet HI plus 1/2 VI squared plus GVI minus all that same stuff, but at the exits. So we have ME times HE plus 1/2 VE squared plus GZE. Okay. This is a good stopping place for today. So I'm going to stop here, but this last page essentially summarizes everything that we talked about today. Okay. Are there any questions?